Okay, so I've written out the first few words on your notes. So what we're going to be doing is we're going to be drawing the actual structures of covalent compounds. So when we do that, they're called Lewis structures, and we use the Lewis dot symbols to represent all of our different elements. So, for example, carbon has 4 valence electrons. And remember, valence electrons are the only electrons involved in bonding. So, if I wanted to draw carbon's Lewis dot structure, I would write the symbol of the element, which is just C in this case. Then I would draw 4 dots around carbon to show its 4 valence electrons. I could have drawn them 2 on each side or 2 top and bottom. It doesn't matter just yet. Yes. The most electrons that you will ever put on any one of the 4 sides of your element is 2. Okay? Only 2 elements per side, top and bottom. So, before we actually get into drawing Lewis structures, let's refresh our memory on ionic and covalent bonds. Ionic bond is the transfer of electrons from a metal to a nonmetal. So we will not be drawing ionic compounds using Lewis dot symbols because we're simply transferring electrons. So this is what sodium, so say we form sodium chloride. Let's see. What's happening is sodium is becoming positive while chlorine is filling up its valence electron shell and it's becoming negative. So chlorine by itself has only 7 valence electrons, but when it forms chlorine minus, it just adds 1. If you are unsure about how many valence electrons are in each element, it corresponds to the group number if you're using the A system. So like this is 1A, 2A, 3A, 4A, 5A, 6A, 7A, etc. So these have 1, these have 2, 3, 4, 5, 6, 7, 8. That's how I get those numbers so quickly. Okay, so if I drew a bond for an ionic compound, there's really no bond. I just transferred electrons. And I told you that if they're in a solid state, it forms a lattice, and it's just alternating by charged particles. We talked about that in the previous chapter. All right, so covalent bond is 2 elements sharing electrons with each other. Why would anyone want to share their electrons with each other? Well, if they can share their electrons, they can all be in a partial content state. So if they all have a completely filled valence electron shell, then they would be happy. So most of the time, the goal is for each element to have 8 valence electrons. There are some exceptions to that, of course, but for a majority of them, that's it. And this is called the octet rule. I was going to mention that anywhere. So, according to the octet rule, elements are satisfied when they have 8 valence electrons. So there are 3 different types of covalent bonds. There's a single covalent bond, a double, and a triple. There is no such thing as a quadruple bond. Doesn't exist. I ask that sometimes and people get that wrong. So that's why I tell you. All right, a single bond. You're sharing 2 electrons. Sharing 2 electrons between two elements. The way I show a single bond, say I have element X bonded to element Y. I do one line that represents a single bond and 2 electrons. How many electrons do you think I share in a double bond?
4.
Yep. I wrote the wrong 2 right there.
I saw that already.
And to show a double bond, it looks like an equal sign. Then the last type of covalent bond is a triple bond, and it is sharing 6 electrons. Between 2 elements. And I would show that with 3 straight lines. Any questions about any of those terms? Okay, well, as you might guess, both elements that you're forming a bond between, each of them are not sharing their electrons equally. So it's not like, give you 50% of my electrons, you give me 50% of yours. Don't happen like that. It's kind of like a marriage.
Right?
Don't work like that.
Those bonds be all over the place.
Right, you are so all this, I can write it down. So what happens is
the male element takes most of
the electrons, it leaves the female with none.
and the female element is left
You leave the female alone with
They're
all the
left with
kids
nothing.
and no one.
Yeah.
Okay.
No offense, guys.
We're talking about elements here.
Yeah. Yeah.
Strictly elements.
You didn't know they had genders?
So what happens is, if I have two elements that are not sharing electrons equally, I form what is called a polar covalent bond. A polar covalent bond means I have an unequal sharing of an electron. Because of that, I'm creating two poles on that bond. So just an example, and I'll tell you how we know this in just a second. Hydrogen fluoride, or it could be, if it was in the water, it could be hydrofluoric acid. But fluorine doesn't share like at all. He takes, but he doesn't give back. So when he is bonded to hydrogen, because he's pulling all the electrons toward himself, he is creating a partial negative charge, leaving hydrogen with a partial positive charge. So that's why it's called polar.
Because partial polar.
Partial charges.
Yeah.
That's
That's how I remember it.
funky looking symbol I have up there is partial. It stands for partial. If you have extensive background in calculus, you take partial derivatives. This is the sign we use. Let me just add this and then I'll tell you, we'll talk about the next part. I keep writing this, but I'm afraid y'all will be like, why does it say by the way? So a polar covalent bond is kind of like an intermediate state between a purely ionic bond, which I'm donating electrons, and a purely covalent bond, which I'm sharing equally. So really, it looks like hydrogen and fluorine are sharing these two electrons, but fluorine's taking most of the electron with it.
No, the intermediate between purely ionic and purely covalent bonds
Is polar covalent.
Okay. I got you.
All right. Well, how do I know who is going to pull more electrons toward itself and who will just be left there to dry? Electronegativity. So this is another trend on the periodic table that we didn't talk about in chapter 3. The reason we didn't is because electronegativity is a man-made concept.
Of course.
I know, right? There's several different scales that you can measure electronegativity, or different people that have measured it different way. The scale we will use is called the Linus-Pauling scale. You don't really have to know that, I'm just telling you. All right, so the definition of electronegativity, I'm going to write that up here. So the definition of electronegativity is the ability of an atom to attract or pull electrons towards itself in a chemical bond. Because of electronegativity, we have polar covalent bonds.
Since fluorides is like 4.0 and hydrogen is 2.1 if you contract, so
Hot fluorine. So how Linus-Pauling made the scale that I put in your notes is he determined which element was going to pull the electrons toward itself the most. Turns out it was fluorine. So he set his scale at 4, and then he measured every other element against fluorine. So fluorine has the highest electronegativity. The trend, if you remember that fluorine has the highest electronegativity.
If the trend goes with the atomic radius.
Yes, it does. But if you remember, fluorine is furthest to the right and it's
the highest
highest up. So that's the way the trend follows.
That's easy to
See here.
but I also have it. And I'll write it immediately on the period.
You're funny. Okay, you'll notice that 3, helium, neon, argon, there is no electronegativity value for them. That's because they're happy the way they are. Krypton and xenon, we'll see in this chapter, even though they're noble gases, and noble gases usually don't react, those two, in certain exceptions, will. Okay, so we use this electronegativity scale here to determine if I have a pure covalent, a polar covalent, or an ionic bond.
We're almost done. Fluorine is the highest of that. Makes it easy to run this around.
Oh, I don't think I mentioned this. These, numbers on this periodic table in your notes, they're unitless. There is no, unit associated with these numbers. If you needed to know that. Alright, so
Well,
what we
there was one that didn't have anything but just the simple, I mean, the simple one that I printed out for us on one of the slides. I was like, does there have anything else in there? I have it.
sometimes I have like weird JPEGs and
Yeah,
they
yeah,
won't
yeah.
print for whatever reason. Alright, so what we do to classify what type of bond we're talking about with electronegativity is we compare the elements' electronegativity values. Classifying bonds by difference in electronegativity, that's where I am in your notes. We take the difference in electronegativity and we apply this scale to it. If the difference in electronegativity is 0 to 0.4, you have a purely covalent bond. You'll also see this referred to as nonpolar covalent as opposed to polar covalent.
Where were you?
Right here under on the first page, there's
Oh,
a
we're still on the first page?
Yeah.
Okay. Classification of bonds, small, intermediate, large.
Intermediate is going to be like 0.5 to like 1.9. That is going to be a polar covalent bond. And then anything larger than 2 is going to be strictly ionic. But you shouldn't have to compare its electronegativities to determine you have an ionic bond.
I remember being very confused, like when she was teaching the polar and the non-polar, like in the very beginning, like the whole class was like
Right.
real confused about the polar and the non-polar.
So I will provide you with this electronegativity chart on the next probably 2 tests. But as we start doing this, you'll kind of figure out what bonds are always polar and which bonds are not. Okay, so the next little arrow there says the larger the difference in electronegativity, the more polar the bond. And the negative pole or end is toward the more electronegative atom. So just a second ago, I did HF, and I told you that it was polar.
Did I do, so, yeah, fluorine is the greatest, okay. So it doesn't go with it's the greater, it goes with the nuclear charge. Like it's parallel with the nuclear charge. Yeah.
His atomic radius
It's
is
good
the
this
other
way.
So I told you that it was polar, and I had a partial positive pole on hydrogen, partial negative charge on fluorine. How do I know that? Well, if we take the difference in fluorine and hydrogen's electronegativity, so if I say 4, that's fluorine's electronegativity, minus 2.1, which is hydrogen's electronegativity, what do I get? Yes. 0.9.
I got 4 minus 2.1 is 1.9.
I don't do math very well in my head. So you'll notice that follows in the intermediate, small, intermediate, and large. I'm referring to the difference in electronegativity.
So which one do you know to pick for like the 4.0 because that's the fullest?
It's the biggest.
It's the biggest because it's got the 8. That one's got 8.
You want no.
Oh.
The biggest electronegativity value.
Oh, okay.
You want to do the biggest electronegativity minus the smallest, so you don't get a negative number. So I know fluorine is 4, hydrogen 2.1, so I say 4 minus 2.1, I get 1.9. That falls in the polar covalent region, so this bond is polar covalent.
Okay. Well, that makes it a lot easier than how we did it.
Yeah, if
When you
you
got the
have your
numbers.
chart.
Yeah, if you got the numbers, yeah. Well, that's I need the chart. That, so that's. Okay. Where's it?
The one on the bottom right of fluorine, the little number written to the side.
I'm ordering this today.
Alright, another way to show whether a bond is polar or not is if it's polar, you use this little arrow here. This arrow, the head of it points toward the pole that is negative. The tail, I've drawn a line through so it looks like a positive. So that's on the positive pole side. So that's one way or one notation to represent polar bond. You could use the partial positive, partial negative, or this arrow. Alright, flip over to page 2. I have notes all over this thing, all over these notes that say add page number. Yes, add page number. Why? I forget.
Yeah.
Alright.
On your 30th year of teaching, you can finally give it back to be the year that you add.
Yep.
Set a goal. Set a goal.
Let's move towards a smaller goal. Let's say 10 years. Alright, I'm skipping over dipole moment and the percent ionic character.
So what if we did we do anything with the large, I mean, that's just saying the larger the electronegativity, the more polar the bond. Nothing.
That's it. So if we skip those first two things, look at example 5.1. All you're asked to do is classify the bond between each pair of atoms as covalent, polar covalent, or ionic. So what you need to do is you need to look up the electronegativity of both elements, take the difference, compare it to this. That's all you're doing.
Fluorine. 3.2.
You know it's in your notes.
So do you say, I mean, can you get a negative? Or do
No,
you
that's
just
why
need to say that, you need to say the highest one is the
yeah,
lowest?
that's why
Okay.
you always take the bigger one.
Okay, that's what I was just saying, yeah. So once we got.
Alright, I went through and wrote in green both elements electronegativity value.
That is not the charge. Oh, you said, I got 3.4 oxygen. Did you say 3.5?
So all of these are pretty easy to just look at and do. If fluorine's 4, strontium is 1, what's the difference?
3 ion.
Here, let me write what is 3. So the En difference is 3. Therefore, it's an ionic bond. Again, I didn't even have to look up those electronegativity values to know that's an ionic bond. It's between a metal and a non-metal. Of course it's ionic. Alright, part B. Nitrogen is 3, chlorine is 3, therefore the En is 0, so I have a covalent bond. Non-polar. And the last one, nitrogen and oxygen. Again, that's easy to look at and do that math. The difference is 0.5, so that's going to be polar covalent. So this is just in case you ever have to identify bonds as polar,
She did it.
non-polar, etc.
They're polar if they have to jump from here all the way over here to the periodic table, and if they're here on the periodic table and they're not, it was like just, we didn't have no numbers.
That's one thing about me. The proof is in the numbers. That's why I like them.
That's what I'm thinking. Why not just teach it like that? But my tutor would say the same thing every time I went in there to get tutored. She's like, why don't you just do it like this? Like, yeah, not this. More accurate and it makes more sense.
All right. Any questions here?
That's straightforward.
All right. Well, we are now ready to start drawing or writing Lewis structures. So let's read through the notes. The first step in drawing a Lewis structure is to draw a skeletal structure. Step 1, we're going to draw a skeletal structure. The skeletal structure is just showing what atoms are bonded to each other. So in these first few examples, we're going to start with a central atom and we're going to bond things to it. So the central atom, how do I determine who is the central atom? Well, the central atom must be the least electronegative out of all the atoms present in this compound. So central atom must be the least electronegative. The reason is because I'm about to bond multiple things to it. So it can't be wanting to withhold electrons. Let me add something here. Hydrogen and fluorine. Hydrogen and fluorine are always terminal elements, never ever central elements. By terminal, I mean has to be on the outside of whatever I'm talking about.
Yeah.
The reason, well, you probably already know why fluorine would want to be terminal. Why?
Because it's just right there.
Most electronegative. So
It's almost a noble gas already.
yeah, but technically we can say that about the other halogens, and
Yeah.
some of them can be
Yeah,
central atoms.
But it's electronegative.
Can y'all guess why hydrogen might be terminal?
Because it could be positive or negative.
Not the reason.
But it can.
The reason hydrogen has to be terminal is instead of 8 valence electrons, it's in the first energy level. So it can only have as many electrons that are allowed in the first energy level. So
It can't be added to.
the most electrons hydrogen can hold is 2 valence electrons. So these 2 atoms are never the central atom, they are always terminal atoms. All right, step 2, once you've got your skeletal structure drawn out, you're going to count the number of valence electrons that is coming from every atom in the molecule. So say I had HF. If I want to count the total number of valence electrons between these 2 atoms, how many does hydrogen have?
1,
Fluorine?
chlorine,
Fluorine.
8. 7. Sorry.
So together, I have 8 electrons to place around these 2 atoms. It's like what they're contributing to the family, basically. The family of elements they're about to form.
Oh, that's cute. But that does make sense.
All right, what if I have an ion? Well, I have to take that into
If you have an ion,
you have to take that into consideration. So if I have a negative charged ion, that's called an anion. I add electrons to the total number of electrons or the total valence that I'm calculating in my step 2. If it is a -1 charge, you add 1. If it's a -2, you add 2, 3, etc. If you have a positive cation, you subtract.
I cannot spell today.
I can never spell. Probably why I haven't finished my PhD yet. I don't really like to
Don't know how to
write.
spell it.
Yeah, I don't know how to spell it either.
Oh, I know, I did my master's on that. It was just so much easy work.
Right.
I mean, all it was, I was paid to do easy work just to get that master's. I mean, I don't feel that I learned a whole lot, but.
All right, so we've drawn our skeletal structure, calculated the total valence. Now we're ready to start connecting these atoms.